Welcome back to the Algebraic Graph Theory Seminar. This week we have Lorenzen talking about spectral properties of exponential distance matrices.
Yeah, thank you so much, Sabrina, for inviting me. I'm happy to be here. I definitely kind of think this is a fun part of the pandemic, if we can say there's such things, that I can be giving this talk here and then just continue to teach my classes later this afternoon. So today I'm going to be talking about spectral properties of the exponential distance matrix. So just kind of a brief overview of what I'm going to be talking about today. First, we're just going to go over a brief introduction of spectral graph theory, which is kind of the larger area of math that this work lives in. And then we're going to talk about the exponential distance matrix. So we're going to kind of talk about two large pieces about today. The first is going to be we're going to find the inertia of the exponential distance matrix for several families. And then we're also going to be investigating some cospectral families for the exponential distance matrix, which I think showcase some of the unique properties of working with this new matrix. All right, so to kind of start off with what spectral graph theory is. So spectral graph theory takes our graph, which we can think of as our collection of vertices and the connections between them. And it kind of helps us start to talk about the structure. Right, so what I mean by that is if we have a graph like we have here, there's maybe some questions we want to have answered about it. Like, how many edges does this graph have? Or how many connected components does it have? And for this simple example here, right, we could go around and we can count our number of edges that we have. We can say I have one connected component and two connected components. But as our graphs get larger and larger, we still want to ask these questions. But the question now becomes, how do we do it? All right, so the idea of spectral graph theory is, okay, well, why don't we take all this graph structure and we represent it with a matrix? Now you might be saying, Kate, this doesn't make that much sense, right? You know, we had a graph, right? And as it's getting larger and larger, our matrix is also getting larger and larger. So we just have moved one problem to the next. But instead, if we look at the spectrum of this matrix or a set of eigenvalues, then this is going to be a smaller kind of set, and we are going to relate that to our graph structure. So just a quick reminder, if I have a matrix and I multiply by a vector x, such that I get a scalar lambda times that vector back, then I'm going to have x as my eigenvector and lambda is my eigenvalue. In addition, all of my eigenvalues are going to be the roots of my characteristic polynomial. So sometimes we'll talk about the characteristic polynomial and coefficients of it, right? And that's exactly the same question as understanding our eigenvalues. So why would we look at our eigenvalues of this matrix? Well, first, they are graph invariant. It means it doesn't matter how I labeled my graph initially. I'm always going to get the same eigenvalues for my matrix. And as far as graph invariants go, compared to some of them, right, this graph invariant is kind of computationally cheap to compute. I think the second kind of more important reason is that they give a snapshot of the structure, right? That's the whole kind of idea behind eigenvalue of a matrix, is that they give a snapshot of the structure of a matrix. And since this matrix is just a representation of the graph, it's also going to be giving a snapshot of the structure of the graph. And I think kind of lastly is that we have a lot of evidence to show that our eigenvalues do relate to different structural elements of the graph. So for example, if I had my adjacency matrix, which I can define to have ijth entry equal to 1 if vertices I and j are adjacent to each other and 0 otherwise. So here I have my graph and here I have my corresponding adjacency matrix. Since vertex 1 is adjacent to vertex 2, meaning they share an edge, I'm going to have a 1 in my 1, 2 entry. Now, this matrix is sometimes called the walk counting matrix, because if I raise it to a power k and I look at the ijth entry, this is going to tell me the number of walks of length k from vertex I to vertex j. So here I have a graph, my graph, and I have different powers of my adjacency matrix, right? And I want to turn our attention to my diagonal entries of a squared. So these are going to be all of my walks of length 2, starting at a particular vertex and ending at that same vertex. And we can notice as we look at the vertices of a graph, that these diagonal entries are equal to my degrees. which makes sense, right? If I start at a vertex, I can walk out on the edge and I can walk right back, and that's going to be my walk of length 2, starting and ending at the same vertex. So this is going to tell us that if I sum my diagonal entries, I am going to be summing my degrees. Well, another way that we can sum our diagonal entries is with the trace. So I can say that I have the trace of my adjacency matrix squared is going to be equal to the sum of my degrees, which we know is going to be twice the number of edges of a particular graph. Now, another way I can always write my trace is I can sum my eigenvalues of that particular matrix. So all of a sudden now here, I have a relationship between my eigenvalues and the number of edges of my graph. And so we are actually going to then be able to say that our number of edges is determined by the spectrum, meaning if we know our eigenvalues of the graph, we immediately know the number of edges that we have. And so this is kind of one of the big ideas of spectral graph theory, right, is that we can relate our eigenvalues or our spectrum to different structural properties of the graph. All right, so the matrix I want to be talking about today is the exponential distance matrix. And to get there, I want to first talk about the distance matrix. So my distance matrix, I want to define have ijth entries be now the distance between vertex I and vertex j, where again, my ijth entry, I'm going to, I want that to be the length of my shortest path between my ijth entry, and I'm going to think about it as counting my edges. So here I have my graph and I have a corresponding distance matrix. Since vertex 1 is adjacent to vertex 2, my distance between these two is going to be 1. So I'm going to have a 1 in my 1, 2 entry. And vertex 1 is distance 1, 2 away from vertex 3. So I'm going to have a 2 in my 1, 3 entry. So one of my favorite things about this matrix is kind of the history of the distance matrix. So it was originally used back in the day when they were thinking about how to set up the internet. And the idea is how could we set up a system, a way of labeling the computers so that they could effectively talk to each other, right? So some things that were important, right, is that every computer had its own label. So if I wanted to send a message to your computer here, that they would know that the right person got the message at the end. Right, and then the other thing is that we wanted these messages to be sent in an efficient manner, right? Is there a way that we can label and kind of say, okay, this is kind of the path you want to be taking in our internet network system. So we're not sending messages around the world 7 times before they reach their final destination. Right, and this was really inspired by Hamming codes on cubic graphs, right, where this is where we are going to with a binary string such that 2 adjacent vertices are only their address is going to only differ by 1 bit. Right. And what was really nice about this is this uses a small amount of data as far as to address. And there's this idea that we can also, it always tells us how we can take our shortest path. Right. So if I'm here at computer 000 and you're over here at 10101, right, we already know that what bits need to change. So we can always kind of take an efficient path. Right, the idea is, can we do this with not just cubic graphs, but can we extend this kind of idea of a Hamming code to any graph, right? But also keeping our addresses at shorter length, right? Anything is possible with infinite length, but can we also keep our addresses small? Right, and this was solved by Graham and Pollock, and they said, hey, if we add in a 3rd bit or like a D for I don't care about this bit, then the distance is again going to be the number of different, the different number of zeros and ones between our 2 address labels. And what this actually does is it takes our distance matrix and it actually decomposes it into 0 and 1 matrices. And they were actually able to find that the length of the address, right, is actually going to be at most max the number of negative or positive eigenvalues of the distance matrix. So within that, they kind of started to explore some ideas of the inertia of the distance matrix, where the inertia is a tuple, telling us the number of negative, 0, and positive eigenvalues. So they found that the complete graph has mostly negative eigenvalues for the distance matrix, and 1 positive eigenvalue, and same thing for our trees on n vertices. In addition, some kind of, I think, a very surprising result for the distance matrix is they found that the determinant of a tree, so this is the product of all of the eigenvalues, does not depend on the structure of the tree. It is only dependent on the number of vertices. So anyway, these are kind of some interesting results related to the distance matrix. So you might be thinking, distance matrix, coolest matrix out there. But there are some limitations, right? And those limitations come for when we have graphs with many components. So we have this graph here. I might be saying, how can this graph have a distance matrix too, right? And in particular, it comes down to what should the UV entry be, right? What is the length of the shortest path between vertex V and vertex U? Since they are in different components, right, we have usually defined this distance to be infinity, which makes it really hard to then put this into a matrix and then find the eigenvalues if we have an infinite entry. All right, so one way we could solve this is with the exponential distance matrix. So the exponential distance matrix, or DQ, I'm now going to define my ijth entry to be a variable q raised to the distance of vertex I and vertex j. So here I have my graph and I have my corresponding DQ matrix. So vertex 1 is adjacent to vertex 2. So my 1, 2 entry is going to be q raised to the 1th power. If vertex 1 is distance 1, 2 away from vertex 3, so I'm going to have q squared as my power. Some things to note about this matrix. First, all of our diagonal entries are going to be 1, since anything raised to the 0th power is going to be 1. If I let q equal 1, then this is going to turn into my all ones matrix, which has very well-known spectrum. And if I let q equal 0, then this is going to turn into my identity matrix, which also has well-known spectrum. And finally, if I let the modulus of q be less than 1, then this is actually going to be a well-defined matrix for disconnected graphs, since then q raised to the infinite power is going to be equal to 0. When q is between 0 and 1, there are some interesting things out there that I'll touch on a little bit briefly later when q is not between 0 and 1. But that's kind of the focus that I'm going to be taking today. So if I say for all q, I'm probably implying it's going to be all q between 0 and 1. All right, so I think kind of the part that I like about working with this matrix, and I think kind of makes it different from other matrices out there, I think is really demonstrated when we try to add a leaf to this graph. So if I want to add a leaf to this graph, what is going to happen to my matrix? Well, what turns out is I'm just going to be taking my, my column of one of my previous entries, and I'm going to multiply it by q. Right, and what's kind of happening here is then the distance from any other vertex in the graph to this new vertex u, I'm going to find the distance to vertex 4, and then I'm just going to add 1 to it. And adding 1 on the exponent corresponds to multiplying by that same base power. So this is kind of really nice, especially if you want to do something like maybe take the determinant of this matrix. So if I want to take the determinant of a graph where I've added on a leaf of vertex u, of my original graph. If I can do some row reductions, since I'm taking my determinant, and I can actually find that this determinant of this graph where I've added a leaf vertex is going to be 1 minus q squared times the determinant of the original graph. So this is a really nice feature. If I wanted to find the determinant of a graph that could be recursively defined as adding on leaf vertices, such as a tree. Right? So a connected graph without a cycle is my tree, and I can immediately get the determinant of my tree is going to be 1 minus q squared to the n minus 1. Right, so this is going to be kind of very similar to the result for the distance matrix, right, where the determinant of a tree does not depend on the structure, it's only going to depend on the number of vertices in the graph. So some other things that have been done. So this is part of a project that I did with Steve Butler and some undergraduate students at an RAU project. So we took this matrix and we completely found the spectrum of the complete graph, the path graph, and the cycle graph. We also found the spectrum of the join and the Cartesian product in terms of the original graphs. And we showed that almost all trees are not determined by their spectral mirroring, results of many other well-studied graphs. All right, and so this was great. And so some things that, that I have done to be taking this further involve looking at inertia. So now instead of kind of actually looking at completely defining the spectrum of a particular graph, inertia is kind of more looking at like a general pattern of the eigenvalues, because we're just looking at the number of negative, 0, and positive eigenvalues. So I looked at 3 families of graphs. I looked at multipartite graphs, trees, and unicyclic graphs. All right, and I'm going to kind of show some results that we have about the inertia of these graphs. So the first one I want to focus on is our unicyclic graph. So a unicyclic graph is a graph with only one cycle. So I can think about it as I have a cycle graph, and then I iteratively add leaves onto this graph to create my unicyclic graph. Right? Since if I ever added a non-leaf, I would create more than one cycle. So the way I'm going to prove this is within 2 steps. The first step, so I'm going to show that it has all positive eigenvalues. And I'm going to do this in 2 steps. The first step is I'm going to show that if a graph has all positive eigenvalues and I add a leaf onto it, then I've only added on a positive eigenvalue. And the second thing I'm going to do is I'm going to show that the cycle has all positive eigenvalues. So then when I add any leaf on to create my unicyclic graph, I'm going to get all positive eigenvalues. All right. So the way I'm going to show that if I add a leaf, I'm going to get all positive eigenvalues is using this idea of interlacing. So interlacing means that if I have a matrix, I have a submatrix, that my eigenvalues are going to interlace each other. Or I can write this series of inequalities relating my 2 eigenvalues together. So what's really nice is if I have my graph and I add a leaf onto it, this original graph is going to form a subgraph for my exponential distance matrix. So I can always write my eigenvalues of my larger graph, which are my lambda k's, as interlaced with my eigenvalues, my mu k's of my original graph. So if I assume that my original graph had all positive eigenvalues, then I get all but 2 of my eigenvalues of the bigger graph are going to be positive. All right, so I only have 1 eigenvalue left to look at. And I'm going to recall that the determinant can be written as the product of all my eigenvalues of the graph. I also know, since I've added a leaf to create this larger graph, that my determinant is equal to 1 minus q squared times the determinant of my original smaller graph. Right? And I know, since my determinant of my original smaller graph has all positive eigenvalues, I know my determinant is positive. And since q is between 0 and 1, I know 1 minus q squared is also going to be positive. So I know this product is going to be positive, which means I have a product of eigenvalues that is positive, and I know all but one of them is positive. Therefore, my last eigenvalue is also positive. All right, so we have that. And then the last thing we need to show is that the cycle has all positive eigenvalues. With the students, the RU, we completely classified the spectrum of the cycle. This is what it is. And there are some kind of neat properties of circular matrices that come out to show that actually all of these eigenvalues are going to be positive. But it's pretty technical, and I'd say mildly to not that interesting. So I am just going to move forward. All right, so unicyclic graphs are going to have all positive eigenvalues. Using the same idea of the unicyclic graphs, we can also get that trees have all positive eigenvalues. Again, where I can add a leaf and I'm only going to add a positive eigenvalue, that one still applies, but now I just have a new base graph of a single edge. And then the other result was multipartite graphs. And it turns out the inertia depends on what Q is. It's not as set in stone as our unicyclic graphs or our trees. So this is kind of the full statement. There's a lot going on here. So what's really happening is I have eigenvalues in my multipartite graph come in one of 3 forms. The first form is I have 1 minus q squared, and this has multiplicity n minus k, where k is the number of components that I have. right? And for when Q is strictly between 0 and 1, these are going to remain positive all the time, right? And so what is happening is when I have Q is close to 0, I have all positive eigenvalues. And then as Q gets closer to 1, a lot of them become 0 for one value of Q and then are going to turn negative, right? Except for these n minus k. These are going to stay positive until Q actually equals 1, and then something else happens. I then have my eigenvalues of my second form, and these have multiplicity pi minus 1, where pi is the number of times that a component size. And so these are also going to be equal to 0 at just one value of Q. And my last ones is I have mine of the third type, which are the roots of this polynomial, and these all have multiplicity 1. And what is happening is we have all of our eigenvalues when Q is close to 0 are equal to n, right? And then as Q increases, we have these special values of Q where we alternate between the eigenvalues of the second kind or the eigenvalues of the third kind equaling 0 for that one value of Q and then being negative for our remaining values of Q. And so that's why we kind of see this alternating between having a pi minus 1 equaling 0 and then negative, or a 1 eigenvalue equaling 0 and then becoming negative, slowly shifting over. A kind of a way that I like to visualize this is if we graphed this, this polynomial here. So again, my eigenvalues are my roots, and it has these asymptotes, which actually happen to be all my eigenvalues in the second kind. So what happens is when Q is close to 0, all of my asymptotes are on one side, and then they're slowly going to shift over as Q gets closer to 1. And so that's where we get these exactly 1 values m equal to Q, and then we're continuing forward. Except for this last eigenvalue, which always has to be positive, and that falls out due to some trace properties. So there's a lot of kind of things going on with this, and anyway, I kind of think it's an interesting result, but it actually mirrors very similarly to finding the inertia and the eigenvalues of the complete multipartite graph for the adjacency matrix. All right, so some kind of further things we could look at. Are there other families of graphs with nice inertia and determinants? One possible candidate is a linear 2 tree. So now instead of adding a leaf vertex, maybe I'm adding a vertex and I'm connecting it to 2 adjacent vertices as we're growing our graphs. So there's definitely some evidence that this might have a nice inertia or a nice determinant. Another question we can ask are there values of Q where our spectrum behaves differently? And this is usually where I end kind of this talk, and I just kind of throw out, Q equals 1/2, things behave a bit differently here. We might notice this is called my fake out ending, because we are now going to be kind of looking at what do I mean by Q equals 1/2 behaves a bit differently. So the evidence with that kind of comes from this idea of cospectral graphs. So anyway, we have some interesting evidence that shows up while we were searching for cospectral graphs. So we are now going to be talking about. Okay, so cospectral graphs. I think first thing we need to do is define what a cospectral graph is. So a cospectral graph is a pair of graphs that have the same spectrum, right? These are called cospectral graphs. So here I have 2 graphs that have the same spectrum for the exponential distance matrix. And these are actually going to be cospectral for any value of Q. How do we know this? Well, we computed out the characteristic polynomial in terms of Q, and it turns out they were the same. So these are going to be cospectral for any value of Q that we have. So you might be saying, oh, okay, that's kind of interesting that if you wanted to find examples of cospectral graphs for the exponential distance matrix, because our cospectral graphs can kind of show us maybe structure that's not preserved by the spectrum. Like for this example here, I only have 2 leaves in my first graph and I have 3 leaves in my second graph, so I could immediately tell that I'm never going to be able to tell the number of leaves from about my graph directly from my eigenvalues. So if we wanted to find more examples, you might be saying, oh, that's interesting that we just computed all of your characteristic polynomials in terms of a variable Q and saw which ones were equal to each other. But that's actually not really how we went about computing our cospectral graphs. Because actually you quickly run out of computing power if you leave Q as a variable. So some workarounds when we did this is we said, hey, well, let's just like choose Q to be some sort of number, right? Find all of our cospectral pairs for that number, right? And then we can then compute our characteristic polynomial from there to see if it's going to be cospectral for all pairs of Q. So if we would then choose some value of Q. So sometimes we would choose something that was very close to a transcendental number, like 72 over 103. And we get so many examples. And it turns out that they were all cospectral for all values of Q. So we're like, wow, that's amazing. We're like, well, maybe let's choose something a little bit nicer, right? You know, having the computer tell us things about the spectrum when Q is equal to 72 over 103 is like kind of asking a lot. Let's try Q equals 1/2. Well, when we did Q equals 1/2, we all of a sudden got examples of pairs of cospectral graphs for Q equals 1/2 that were not cospectral for all values of Q. And no matter what other numbers we tried, Q equals 1/2 was the only value of Q where we found pairs of cospectral graphs only for Q equals 1/2. Yeah. And so again, this is our only tested value. You know, it's not like we only tried three numbers. We tried a lot of different numbers and this kept popping up. So here's an example of a pair of cospectral graphs that are cospectral for only Q equals 1/2. So I have over here my friendship graph, and then I have this other graph with an isolated vertex that are only going to be cospectral for Q equals 1/2. Again, how do we know they're only cospectral for Q equals 1/2? Well, we computed our characteristic polynomial in terms of Q of our first graph here. And then we compared it to our characteristic polynomial of our second graph. And if we subtracted our two polynomials, that polynomial only had a root of Q equals 1/2. So that was definitely, then the coefficients are going to equal 0 when Q equals 1/2. So that's going to kind of help us kind of notice a few patterns that we had. So these are some patterns we noticed when we were looking at our cospectral graphs. The first one we noticed is, hey, actually it turned out that anytime we found paragraphs that were cospectral for some value of Q and both graphs were connected or had the same number of components, they were going to be cospectral for all values of Q. And if we had a different number of components, that's the only time we ever found graphs that were going to be cospectral for only one value of Q, and that value was going to be 1/2. And in fact, that these examples we found tend to kind of lead to nice patterns if we increase the number of vertices. Lastly, this is we unrestricted Q from being between 0 and 1. We actually were able to find other examples of cospectral graphs that are only cospectral for one value of Q. So we found one for when Q equals 3, when Q equals -2, when Q is equal to plus or minus I. So this is just some personal beef I have with like the last point, is that our matrix should not be defined for these values, because the whole idea is that if I had a different number of components, I wanted to have Q in between. I wanted the modulus Q to be between 0 and 1 in order for this matrix to be defined for multiple components. Now, some of my co-authors said, no, that's fine. We can let then Q, we can then unrestrict it once we use the restriction to create our graph, which is fine. I mean, it's a choice. So just know that that is out there. If you're like, wow, Q equals 1/2 is like so amazing. Just know that there are other interesting values of Q out there where this kind of cospectral for only one value of Q seems to be happening. But if we're just restricting ourselves to the modulus, we only have ever found Q equals 1/2. Okay, so I said that there were some nice patterns when we increased our number of vertices. So here was kind of the two cospectral graphs I had before. And I increased the vertices. I then found this pair of graphs with a different number of components, only cospectral for Q equals 1/2. And this is our next pair and our final pair here. So this is clearly adding to like, okay, there's something going on here, and I wanted to investigate, right? We seem to have kind of, there's this path growing, right, out on this side from this isolated vertex, right? And there's also, there seems to be this path expanding within our friendship graph. And so I made a very large declarative statement saying, exploring this pattern will give me enlightenment as to why Q equals 1/2 is interesting. All right, so we're about to see if this is true. So I want to go about and try to explain why these two graphs are cospectral and see if I can kind of extrapolate some kind of interesting constructions from there. So first thing I want to do is I want to kind of just kind of like redraw these graphs in a way that I can kind of talk about this pattern. So my first graph I want to talk about, which is this bottom pair, I can always rewrite it as two K2s joined to a K2 plus some path of length M out here. And I want to show that this is cospectral to if I had two K2s joined to the end of a path and then another K2 joined to the other end of the path, right? Kind of again, trying to relate some of the structure together to see where have I maybe changed some things. All right, so as far as ways that we can show graphs are cospectral, we're kind of limited to like one of three techniques. The first is we could find a similarity matrix between our two matrices. This is really great if we have the same number of edges in both of our graphs, because a lot of times what we're doing is we're kind of like just moving the things around. Another thing we could do is we could do a manipulation of our eigenvectors. This is a very common in the normalized Laplacian, right? To have the eigenvectors of one matrix and be able to show some sort of transformation that they are the eigenvalue vectors for the other matrix. And then the last is do kind of some direct computation of our characteristic polynomial. And this is the one we are going to be doing today. Why are we going to be doing this? Well, it's kind of because I have this top graph up here, right, where I have this graph on only 6 vertices. I can compute its characteristic polynomial. And then I also have my path over here. And if I have two disconnected graphs, my characteristic polynomial with a large graph is the characteristic polynomial of the two multiplied together. So that's kind of why I'm going to be moving in this last direction. So that's going to be leading me to want to find the characteristic polynomial of this bottom graph. Okay, so let's go ahead and do that. So here I am just writing out my characteristic polynomial. I'm doing taking my determinant of x minus my DQ matrix. Since I have most of this kind of, since I have this kind of nice pattern going around my outside, I can actually do a lot of row operations to reduce this down. M1 and M2 are both of kind of finite size, so I can keep track of what's happening as I'm kind of doing some row operations. And then I just have these little minus q x's on either side that I need to be dealing with. But I can expand this out pretty straightforwardly and get this expression here, where I can get that I have some polynomial times my characteristic polynomial of my path on m vertices minus some other polynomial times some stuff times my characteristic polynomial of my path on m minus 1 vertices minus x squared minus q squared of my characteristic polynomial of my path on m minus 2 vertices. When we completely found the spectrum of my path on m vertices, it actually is a kind of a recursive definition. So I can apply my recursive definition by getting these two coefficients to work out only when q is equal to 1/2. And so then I can essentially kind of factor out this characteristic polynomial on m vertices of the path on m vertices. And then I'm left with is these two other polynomials. And when are these going to be when is this going to be the characteristic polynomial of that other graph on 6 vertices? Well, actually, again, only when q equals 1/2. So there's 2 times we use q equals 1/2 in order to show that these two graphs have the characteristic polynomial. So not a lot of enlightenment. It just kind of was like, well, this is when the algebra works. It's very reminiscent of many research meetings I had with my advisor of like, well, q equals 1/2 is special because, as you know, 4 divided by 2 is equal to 2. And it was just, it was a lot of that type of talk. What is interesting though about this construction is that this was not the only family that we had a different number of components with Q only equals 1/2. If instead of 2 K2s, I put in a K4 and I had an empty graph here, and I joined them plus my path as cospectral to I have one of them joined to one end of my path and the other graph joined to my other pair. What is interesting if I go back here is that these two pieces are going to be the same. So there is possibly something going on. Again, it's not as enlightening, I think, as I wanted it to be. Okay, so just kind of some concluding remarks. So one thing I really like about the exponential distance matrix, and I like working with it, is this kind of multiplicative nature. You know, kind of when I had that characteristic polynomial and I said, oh, I can, since I'm taking my determinant, I can use these row operations. And those work really nicely because if I want to increase my distance, I am multiplying a column of the matrix by a value instead of like adding a 1 to it. So for when we're doing any matrix arithmetic, right, having this kind of multiplicative property that's going on when I'm creating these extra distances just makes this like very beautiful way of like being able to like reduce it down. So just, I think that's like, this is what's very, I find compared to working with other graph matrices, the exponential distance matrix is unique in this way. Another kind of question that I have is like, you know, are there other values of Q, you know, within the modulus of 1 that do behave differently than others, right? We kind of saw that there's Q equals 1/2. What are some reasons behind that? And, you know, are there others out there? How could we go about finding it? Just some kind of interesting questions I have. All right, so I think I'm going to end it there, but thank you everyone for being here and for listening to me talk about the exponential distance matrix. And I'd be happy to answer any questions.
Thank you for the talk. Are there any questions?
I think the Q equals 1/2 is very intriguing. Can I see that you use a lot of K4. At least it looks like a K4 in your construction. So if you replace the K4 by, say, K5 or other complete graphs, do you expect to see a different value of Q that comes up, or have you played with it?
Yeah, so yes, I think the time I was playing around with it, it has been it's been a while. I don't think I haven't tried putting in different graph, like a K5 in there. What it was interesting is, kind of like what two graphs kind of almost like put in the two circles. They did seem to be like either this, like a complete graph or like copies of complete graphs or empty graphs were kind of the two things that we were seeing. I mean, it's just again of kind of like how, just trying to generate examples and just kind of just trying things out can even be difficult just because of how I don't want to say like, oh, there's too many vertices, but yeah, just there are some kind of different things to explore.
Thank you.
There's a question in the chat. Is there a reason why inertia is called that way?
I am not exactly sure why inertia is called inertia. Yeah, I'm sorry.
It's a very old term, and it goes back at least to Sylvester, who was very fond of making up names for reasons which other models couldn't always follow. That's related to the fact that if you have an matrix A and you have an invariable matrix G, then then G transpose and A have the same inertia. So the technical term would be that it's invariant under congruence. So the map takes a matrix A to G. G transpose is a congruence map, so a similarity map. And congruent matrices have the same inertia, and that's possibly where the motivation was.
I have a question.
Yeah.
Can you hear me?
Yes.
Okay. So I noticed that your exponential distance matrix for certain graphs, such as the distance regular graphs with classical parameters, that exponential distance matrix is very close to one of the primitive idempotents. In fact, the Q polynomial idempotent for the adjacency matrix. More specifically, that exponential distance matrix is a linear combination of the all ones matrix J and this special primitive idempotent. So it's just striking to me that, this connection between what you're doing and these primitive idempotents. One observation is that the exponential distance matrix, now has a very small rank relative to the number of vertices for this type of graph. I don't know, has this come up? Is this relevant to your research at all?
Yeah, so I do know that was one of the ways that we kind of, when I was kind of initially working with the RU group, that we were working with the matrix and trying to classify the spectrum for special cases. And yeah, we're just kind of like trying to look at some properties. Yeah, when the diameter of the graph is 2, right, that there's ways to write it in terms of like the adjacency matrix, with the linear combination of the adjacency matrix and the all ones matrix. And so that's actually one of the ways of like when the diameter is equal to 2, we can relate a lot of kind of structural properties between the two and just essentially kind of like pull a lot of results immediately from that. But I guess I have not looked at particular having a low rank and what would that mean for the matrix.
Or you could ask, for what graphs does the exponential distance matrix turn out to be a linear combination of 2 primitive idempotents for the adjacency matrix?
Yeah.
So that, the all ones matrix and then one other primitive idempotent. That would be, so you're going to catch in such a classification, you're going to catch a large number of distance regular graphs, those with classical parameters, if you pick the right Q. And it would be interesting to see what other graphs showed up in such a classification.
Right. Yeah. 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 Thank you. Thank you for bringing that up.